You know, every single time we get on a plane, we're putting our trust in materials that have been engineered to be just about perfect. But what happens when one of the strongest, most dependable materials in the world is hiding a dark secret, a tiny, microscopic flaw that has catastrophic potential? Today, we're going deep, investigating a hidden danger that lurks inside the very metal holding our modern world together.
Okay, so let's get right to it. Meet our main character, if you will, AA7075. This is an aluminum alloy, part of the 7000 series, a family of metals that are famous for their incredible strength. You can really think of it as the superhero of structural materials.
And its job? Well, it's absolutely critical. AA7075 is a cornerstone of the aerospace industry. It forms the structural backbone of aircraft wings, the fuselage. Its strength-to-weight ratio is just legendary. It's the magic that lets a colossal machine like a passenger jet defy gravity and keep us all safe 30,000 feet in the air.
And here's where our story takes a turn. This amazing strength is masking a profound weakness, a vulnerability that only shows up under the most intense pressure, during the very process that's meant to join it all together, a flaw that can and absolutely does cause it to break.
And this really gets us to the heart of the mystery we're unpacking today. How can something so incredibly strong also be so fragile? What invisible force is at play here, and how in the world do we find it before it's too late? Let the investigation begin.
So our investigation kicks off by identifying the scene of the crime. But it's not a place, it's a moment in time, that exact instant when this fortress of an alloy lets its guard down. This flaw, this villain of our story, it has a name: hot cracking. Just picture it. Metal is cooling down from a molten liquid state and turning back into a solid. There's this in-between phase, what engineers call the mushy zone, where the material has basically zero ductility. It can't stretch, it can't give. So if it gets pulled on by stress at that exact moment, it doesn't bend, it just tears apart.
And this quote from the research just nails the problem perfectly. It says that the very act of fusion welding, melting the edges of two pieces to join them, creates the absolute perfect storm for this kind of failure. The process that's supposed to build strength is the very thing that introduces a fatal weakness. It's a paradox.
Okay, so if welding provides the opportunity for the crime, what's the motive? To figure that out, we have to look inside the alloy itself. We need to examine the elements that give it that legendary strength in the first place. These are our usual suspects.
Now, this is where it gets really interesting. Let's look at the lineup. You've got zinc, that's the main muscle, the primary strengthener. Copper is in there, adding hardness. But our investigation? Well, it pretty quickly zeroes in on two key players: magnesium and silicon. The research shows that at the specific amounts found in A7075, they're the ones who are really increasing the risk of hot cracking. They're our prime culprits.
It's really a classic case of too much of a good thing, or rather, the wrong amount of a good thing. These elements are vital for the alloy's amazing properties, but their specific percentages create this chemical cocktail that makes the material brittle at the worst possible moment. So we've identified our suspects. Now we have to prove it.
To be sure about our suspects, scientists need a way to force this flaw out into the open. They need to put this metal under so much stress that it literally has no choice but to show its weakness. This is the interrogation.
The technique they use is called the Houldcroft test, and honestly, it's just brilliant. First, they take a piece of the metal and cut it into this fishbone shape. You see those slots on the side? They get longer and longer, which means the piece gets more and more flexible as you go down. Then they run a weld right down the center. At the top, where it's rigid, the stress has nowhere to go, so a crack forms. But as the weld moves down into the more flexible area, the stress eases up and the crack just stops in its tracks.
That crack, its length, that's the confession. It is a direct, measurable piece of evidence of how susceptible this material is to failing. The longer the crack, well, the more guilty the alloy is of hiding this dangerous flaw.
So, the original AA7075 went through the interrogation, and just as expected, it cracked under the pressure. But the real point of all this wasn't just to prove it was weak, it was to find a new formula that wouldn't be. And this brings us right to the climax of our investigation.
The researchers cooked up 4 new versions of this alloy. Each one had slightly different amounts of our prime suspects, magnesium and silicon. Then they put every single one through that same grueling Houldcroft test. The big question was, could any of them actually hold up?
And here are the results. It's pretty dramatic. The original AA7705, look at that, a crack sensitivity of 75.4%. That's a major failure. But then, look at the new formula. Its crack sensitivity plummets to just 49.5%. This is a huge breakthrough.
Let's just put a number on that. That is a 34% reduction in its tendency to crack. The new alloy didn't just bend under the pressure, it fundamentally resisted breaking in a way the original simply couldn't. It passed the interrogation with flying colors.
And now for the big twist. What was the secret to this winning formula? You're not going to believe it. It was more of the suspects. By upping the magnesium to 4.5% and the silicon to 1.5%, they actually moved the alloy out of that dangerous cracking zone. It's just a fantastic reminder that in metallurgy, sometimes the poison is actually the cure.
Okay, so we have a solution, an unbreakable formula. But the final piece of this puzzle is understanding why. Why does it work? What is actually happening at the microscopic level that makes this new formula so much tougher? It really comes down to teamwork. The extra magnesium makes the alloy more flexible, even at those dangerously brittle high temperatures. The added silicone helps create a finer, stronger internal structure. But the real magic is what they do together. They create more of this low melting point liquid that can flow into any tiny tears as they start to form, essentially healing a crack before it even has a chance to grow. It's incredible. And you have to realize, this discovery is so much bigger than just this one alloy. It's a blueprint. It teaches us how to look deep inside a material, find its hidden weak spots, and re-engineer it from the atoms up to be safer, stronger, and far more reliable.
And that really leaves us with a final, lingering thought. This entire investigation uncovered one microscopic flaw in one single, critical material. It really makes you wonder, what other invisible breaking points are out there, right now, hiding in the metals, the plastics, the composites that we all rely on every single day? The hunt is always on.